Okay, so we are recording. Good afternoon, everyone. My name is Dr. Francisco Muller Sanchez, and I'm an assistant professor at the University of Memphis. And I am an observational astronomer who is going to use the James Webb Space Telescope in a couple of months for observations of supermassive black holes. So today, I'm going to talk about one of the most ambitious projects in the history of NASA. It is certainly the most ambitious astronomical project in the history of NASA. And why do I say that it is the most ambitious project in astronomy? Well, it is because it is the largest space telescope that has ever been built. So building the largest telescope, of course, offers several technical or technological challenges for which we have invested a lot of resources and a lot of time. And at the same time, the science that we expect to do with the James Webb Space Telescope is going to be unique and transformative. We expect that the James Webb Space Telescope, or JWST, as I'm going to refer to the telescope for the next 30 minutes, it is going to be the most transformative telescope in the history of mankind. So we are going to discover many new things about the universe, and it will revolutionize the field of astronomy in a similar way as the Hubble Space Telescope did 30 years ago for many areas of astronomy. Okay, so this talk is going to be divided in two parts. In the first part, I'm going to talk about the characteristics of JWST. So some of the important properties like the telescope, the instruments, the things that we can observe. And the second part, I will talk about my two research programs that have been accepted for observations with JWST. So some concrete, real programs that JWST is going to do in the next few months. Okay, so let's start talking about the James Webb Space Telescope. So what is the James Webb Space Telescope? Well, as it says here, it's a mission to seek light from the first galaxies in the universe and to explore distant worlds. Now, it doesn't mean that JWST is only going to do that. We say that JWST is an all-purpose mission because we can observe all the objects in the universe. So we have, when you observe the sky at night, you see planets in the solar system, we will observe them with the JWST. We see stars, we will observe thousands of stars with JWST, and planets orbiting around other stars as well. You see galaxies, we will observe thousands of galaxies. So basically everything you see at night, there are astronomers who are going to observe those objects with James Webb. That's why it's going to be used by thousands of astronomers around the world. And it's a project led by NASA in partnership with the European Space Agency and the Canadian Space Agency. Now, where does the name come from? I mean, we know there is a space observatory, it's a telescope that is going to be on a satellite or on a spacecraft. But why is it called the James Webb? Well, James Webb was the second administrator of NASA from 1961 to 1968, and he oversaw many NASA missions. Here we can see some of them to other planets in the solar system like Mercury or Mars, but also he oversaw the Apollo program, which, as you know, is a very important program in the history of NASA. But I would say that the reason why we decided to put his name on this mission, on this telescope, is because of the last point that is mentioned here. he insisted that NASA have a strong science program. So that's why, I mean, he was the second administrator, but we didn't choose the first administrator or the third or the fourth. And it's because in the 50s, before James Webb, NASA was a very important American institution building new rockets and satellites and technological advances, but it was not really doing a lot of science or pure science as it is nowadays. So James Webb really insisted that NASA actually is an institution here in the United States that will be responsible of a lot of the science we do in many areas. It can be physical sciences, natural sciences, life sciences. NASA covers all sciences that we do as humans nowadays. So James Webb insisted that that should be one of the priorities of NASA, and not only build rockets or other vehicles to travel around the world or to go to space. So in fact, that's what is NASA right now. NASA is doing more science in addition to the other programs, building rockets or spacecrafts, etc. But it's mostly dedicated to science. So that's why this telescope has his name. Now, what will JWST do? Well, it will study every phase in the history of our universe. So we start in the left panel where we have very distant galaxies, or we will observe the light from the first galaxy. So this is, of course, a new area, and we will observe for the first time the light from the first galaxies that were formed in the universe. Then the second panel shows the assembly of galaxies. And that is just how all the matter that exists in the universe came together to form galaxies. And as we know, inside galaxies, there exist millions of stars and planets, like we know here in the Milky Way galaxy where we live. It's our galaxy, the Milky Way. The solar system, the sun is just one of millions of stars in the Milky Way galaxy. So James Webb will help us to understand how galaxies are assembled and what are the important components that create the galaxies that we see, like I was saying, every night when we look at the sky that we see in the universe. It will also tell us in panel 3 about the birth of stars and planets. So how the stars are created and how do planets also are created and how they orbit other stars, like we know it happens in our solar system. So is the origin of other planetary systems similar to the planetary systems that we have, or the planetary system that we have here on the solar system, the 8 planets that we know in our solar system? So it will help us to answer those questions as well. And finally, in the 4th panel, we have planets, solar systems, and the beginning of life. So James Webb is going to be able to see individual extrasolar planets or planets that are not part of the solar system and study their chemical composition, maybe their atmospheres or other physical parameters that will help us to understand if there is life in those planets or not. So this is a very important question for mankind. Basically, the question is there life in the universe besides the life on Earth that we know that happens here in our planet, in the solar system, but we will know if there is life in other planets. And as it is now one of the priorities of the James Webb Space Telescope, we will probably learn in a couple of years, maybe, or maybe by the end of this decade, maybe we will be able to find another planet with life. So it's just a matter of time. That's what we currently believe. So in many aspects, JWST is a scientific successor to Hubble. So here there are 5 parameters that compare the Hubble mission or the Hubble Space Telescope with the Webb Space Telescope. Let's have a look to the numbers here. So the mirror, the size of the mirror of the telescope is approximately 8 feet for Hubble, and it will be 21.3 feet or 6.5 meters for James Webb. So it's a factor of almost 2.5 larger diameter of the Webb Space Telescope compared to the Hubble Space Telescope. So we have a larger area, which means we can detect more photons, more electromagnetic radiation, and we say that it will be a more sensitive space telescope. Now, the length and weight, you can see that actually James Webb is a little bit larger, 22 meters compared to 13 meters of Hubble, but in weight, it's less massive. It's 6,000 kilograms versus 11,000 kilograms of Hubble. Now, the next 3 parameters are actually related because, as it says here, the Hubble Space Telescope observed galaxies in the ultraviolet, visible, and near-infrared part of the electromagnetic spectrum. That means wavelengths between 0.1 to approximately 2.5 micrometers. And then Webb is going to use the visible, the near-infrared, and the mid-infrared part of the electromagnetic spectrum. That means from 0.6 to 28.5 micrometers. Now, these differences in wavelength, of course, is important for astronomers because we can observe different species of gas and dust particles and emission from stars at different wavelengths. So what we see, for example, at 1 micron is different to what we see at 5 microns. So JWST is going to open new windows to observe the universe. That's what we call the infrared part of the electromagnetic spectrum, from 0.6 to 28.5 microns. So I will come back to that in the next slide. Now, the location, Hubble is orbiting the Earth at approximately 570 kilometers from the Earth, so it's moving around the Earth in that orbit. But James Webb is going to be located at an orbit that we call L2, that is at 1.5 million kilometers from the Earth. So it's a very different orbit. And the reasons why we are doing this first is because of the wavelength. So remember, we're observing in the infrared, and the infrared is very sensitive to temperature. So having the telescope near the Earth will be influenced by the Earth's temperature and, most importantly, by the sun. So we want to put the telescope far away from the sun so that it doesn't get very hot. And that's related to the last parameter that you see here. The temperature that the telescope will be working is approximately minus 370 degrees Fahrenheit or minus 230 degrees Celsius. And Hubble is working at 21 degrees Celsius or 70 degrees Fahrenheit. So we say that Hubble is a warm or hot telescope, whereas James Webb is going to be very cold. And that's very important for infrared radiation. So what is infrared light? Well, infrared light can be interpreted as heat. It's the light that is produced by objects due to their temperature. And we know that the objects here in the sun, I mean, you see an example here of a cat, but everything that has a temperature between 0 degrees Celsius approximately, or 5 degrees Celsius to 40 degrees Celsius, radiating infrared light. That's what you see here in the cat. You see the different regions where his body is cold, but then the face and the eyes and the ears are hot. So the temperature of those areas are hotter than the rest of the body of the cat. So our eyes aren't sensitive to these wavelengths. We cannot see infrared light with our eyes, but we can see it through special instruments that are installed, for example, in infrared cameras, or that will be installed in the James Webb Space Telescope. So as you can imagine, we will see things that visible light cannot see. So with our eyes, with Hubble, we could see some things, but now with James Webb, we will see other things that we are not able to see with Hubble or with other visible light telescopes. But the infrared light has also other advantages, and it's that it's transparent to smoke, fog, and dust. So at these wavelengths with infrared light, we are not so much affected by what we call extinction or attenuation, because light is transparent, infrared light is transparent, or materials are transparent. These materials, smoke, fog, and dust, the clouds here, to infrared light. So this is another example of infrared light. You see a glass with hot water, and that looks red and white here, whereas we have a glass with ice, with cold water, then it looks dark. With an infrared camera, it looks, well, dark blue, bluish, and that's the infrared radiation from a glass with hot water and a glass with cold water. Okay, so a comparison of Hubble and Webb. We are comparing the size of the telescope, the primary diameter of the telescope. So Hubble has a diameter of 2.4 meters, and James Webb has a diameter of 6.5 meters. That translates that in a surface area, all the area that it covers the telescope, Webb is 6 times larger than Hubble. This is a comparison of the two telescopes for scale. So in the left panel, you see that the size of the James Webb Space Telescope is comparable to the size of a tennis court, the length, so 70 feet approximately, whereas Hubble is 43.5 feet and is comparable to the size of a school bus. So James Webb is much larger. But the important thing is on the right panel, the comparison of the two primary mirrors. JWST has a primary mirror that is 6 times larger in surface area, than the Hubble primary mirror. And you can see here the comparison of the two telescopes. So we have seen that James Webb is a very large telescope. Like I said, it's the largest space telescope that has ever been built. So it cannot fit inside any of the rockets that exist on Earth, either, I mean, from NASA or the European Space Agency or Russians. We do not have that technology where, or we do not have those rockets where we can put something the size of a tennis court inside the rocket and bring it to space. So the telescope has to be folded up like an umbrella. And that's what you see here. We will use an Ariane rocket from the European Space Agency to launch the telescope, and we have to put the telescope folded. So it's going to be much like a transformer. We will keep the telescope enclosed inside the rocket. That's how it's going to be traveling to space, to the orbit where it will be taking observations. And as you can see here, it's going to be folded in the rocket. And then when it arrives to its destination, it will just open up like a transformer. So that's what will happen in a couple of months. So right now, Webb is set to launch on top of an Ariane 5 rocket from the European Space Agency on December 18, 2021. And it will launch from the French Guiana in South America. And the reason is because we want to be closer to the equator to reach the orbit where James Webb will be located. It's just more efficient and it requires less resources and money, and for the rocket it's easier to be launched near the equator than from any other latitude on Earth. That's why the European Space Agency uses the French Guiana to launch many telescopes or satellites near the equator. And then it will undergo a month-long travel to reach the 1.5 million kilometer journey to its destination at the second Lagrange point of the solar system. And like I already explained, we are traveling that large distance to that point for two reasons. One, we want the telescope to be in an area, in a region where there is not so much infrared radiation, so not high temperatures, because this is going to be an infrared telescope. So it won't be affected too much by other planets or by the Earth or by the sun. Although we will still receive light from the sun, and that's what we're going to see in the next slide, but it's much more reduced. And also, it's going to be in a region that is isolated. So there are no planets or moons or anything in that point. So it will be much more efficient. It will be taking data all the time. Hubble, that is orbiting the Earth right now, has some periods where it is blocked by the Earth and it cannot look into specific area of space. So putting this telescope in that region of space will have an undistracted view, an unblocked view of the universe all the time. So that's another reason why we are putting the telescope there. And this is how it's going to look in its orbit. So you can see three main parts of the James Webb here. We started here. Let me start a simulation again so that you can see. We have the optical telescope element, which is the primary mirror and secondary mirror and everything. Then you have the spacecraft element that has the sun shield and other instruments for communications mostly. And then what we see right now in the Zoom is the integrated science module, which are all the instruments that astronomers will use to observe all the objects in the universe. So here we are mentioning all these instruments: the mid-infrared instrument, the infrared spectrograph, near-infrared camera, guidance sensor, near-infrared imager, and spectrograph. So these are all the instruments that will be part of James Webb and that we will be using for observations. Now, one more thing I want to point out is that there are solar panels at the bottom of the telescope. You just saw them now, and this is a shield that will protect. Let me put pause. Well, let me go back here. So you can see now the solar panels. These are the blue structures at the bottom of the telescope, because James Webb is going to be receiving energy from the sun and then converting that to electricity. And then we need solar panels. So these are all the solar panels from James Webb. And then the structure that you see here, it's actually a sun shield. Let me put pause now. Everything that is under the mirrors, this is the primary mirror, and all this structure is a shield that will protect the telescope from the heat from the sun. So we have solar panels that actually will use the energy from the sun. And then on the top area of the telescope or the satellite, we will have sun shields that protect from the light from the sun and the heat from the sun. That's the sun shield. And then we have the telescope on the top part, which is going to be cooled down to minus 270 degrees Celsius. Okay, now we have some images of the telescope in the lab. So right now the telescope is in California. They are doing some final tests in the it's Norman group. So that's the testing facility in California. And you can see the primary mirror in this image in the lab. Now you can see how the fully tensioned sun shield, remember the sun shield is here at the bottom, it is fully tensioned. So it's when it opens in space, it will look like this. So this is already fully tensioned for several tests. And then we have another image here with the wings deployed. So like I mentioned, like a transformer, that it will be folded and then it will just open when it reaches its orbit. And like I said at the beginning of this talk, Webb is a product of the United States, Europe, and Canada, where many institutions, you can see here some of the institutions that are working for the design and the construction of the telescope. Okay, so if you want to learn more, here there are some links from NASA, some scientific links that you can follow and just see more about them, more images about the telescope, or learn more about telescopes and the science that we will do with James Webb. You can go to any of these links that you can see here. And if you see this talk later, you can just follow these links. And also in social media. So there is Facebook, Instagram, and Twitter at NASA Web, and all the other links here. Okay, so I think there are some questions here. So I finished with the first part of the talk. So how big is the Webb telescope when the wings are deployed? It's the size of a tennis court. So it's more than 70 feet long, and in the other direction is 40 feet approximately. Okay, so now we'll continue with the second part of the talk, where I'm going to describe the research that I do, and it is related to high spatial resolution studies of supermassive black holes and galaxies. So as I said at the beginning of this talk, this is, let me just see, I think there is another question. Why are infrared observations important to astronomy? Well, as I already said, if we look at different wavelengths of light, we can see different things that we wouldn't be able to see just with the visible part of the spectrum that is from 0.3 to approximately 0.8 microns. Specifically in the infrared, we are able to see the emission from gas and dust at temperatures between, like I said, 0 approximately to 40 degrees Celsius. So all that gas, it's now, we cannot see it in the visible part of the spectrum. It's just there, but we cannot see it. But in the infrared, we will be able to see that with James Webb. So that's why it is important. And in fact, that's related to the image that you see here. Everything that you see here, except for stars usually look like point sources, but all the red color, blue color, etc., that's emission from gas. So if we were looking the optical, we would only see the stars, but thanks to the infrared observations, we can see all the gas that is around this galaxy. And that's why infrared observations are very important. Okay, so I was just saying that my group at the University of Memphis and we have 2 accepted James Webb proposals. It means this is science that will be done with James Webb in the next couple of months, and they are related to the studies of supermassive black holes. So just very quickly, as probably some of you know, a black hole is defined as a region in space where the force of gravity is so strong that nothing can escape from it, not even light. And that's why they are called black holes, because they are totally black and dark. We do not see light coming from the black hole. And the name hole, it's just an analogy to a situation that describes an object, like I said, where gravity is so strong that everything that enters to the black hole is just eaten by the black hole. That's the term we use. The black hole feeds from the material around the black hole. So there are many things that we don't know about these objects, but there are a few things that we know. One of them is that supermassive black holes are found in all massive galaxies. So we have observed thousands of galaxies in the universe, and we have found a supermassive black hole at the center of each galaxy. Now, how do we know this? Well, we have obtained observations of the matter that is orbiting around the supermassive black hole, and we see that that produces the most powerful objects in the universe. So that's why supermassive black holes are interesting, among many other things, is because they are the most powerful objects in the universe. And we can see the light from the matter that is orbiting around the supermassive black hole. But also, we can see the gravitational influence of the black hole on the stars and the gas and all the matter that is orbiting around the black hole. And that's how we know that they exist. And the best example is the black hole at the center of the Milky Way in our galaxy. This is a view of our galaxy in the infrared, exactly what we are talking about. It's seen edge on, so the galaxy is here at the center of the image. And then if we do a zoom to the central region, we see a lot of stars, and we have measured the orbits of those stars. So what you see here in this animation are the stars orbiting the center of mass of our galaxy. That's indicated with the red cross. So you can see there are 5 stars here. We have measured the orbits of these stars. These are all data points, what you see in yellow. So it's real data. And you can see that they create perfect elliptical orbits, or almost perfect elliptical orbits. So then we can use very basic equations of Newtonian mechanics and Kepler's laws of motion, and we can estimate the mass of the central object, the object that creates this force of gravity where all these stars are moving around, and that has a mass of 7 million solar masses. So it's the mass of 7 million suns in this small area. Now, for comparison, you see the size of the stars. This is one star, this is another star. We have 5 stars here. That's the size of one star in the galactic center. Now imagine 7 million stars. They will occupy a huge volume. I mean, it's we cannot even imagine in this small region having 7 million stars. So the only object that can create that very large mass in a small volume, a mass of 7 million solar masses, is a supermassive black hole. So that's the best evidence we have for a supermassive black hole in the universe, and is the black hole at the galactic center of our galaxy. And in fact, this is the experiment that won the Nobel Prize in Physics last year. Exactly what you're seeing right now is the experiment that won the Nobel Prize in Physics. And the person who won the Nobel Prize was actually my thesis advisor, Dr. Reinhard Genzel. I was a student of Dr. Reinhard Genzel, and he has been working on this for more than 30 years. Okay, so like I mentioned a few minutes ago, there are objects, supermassive black holes, that produce a lot of energy, a lot of light, and they are called active galactic nuclei. So that's another way that we can study black holes, due to the light of the material that is orbiting the black hole. That's what you see here in this image. You have the black hole at the center, and then you have a lot of material moving around the black hole that's represented with yellow and red colors. And that's the light we see from the black hole. So these objects, like I said, are the most powerful objects in the universe. And because of the light that they produce, they help us to prove something that we call the coevolution of supermassive black holes and galaxies. So you see here a plot where you have the velocity of the stars and the mass of the black hole, and you see that there is a good spatial correlation, a good linear correlation. And that was surprising, because you can think of the black hole being the size of a penny. That's a comparison we do. Imagine something that has the size of a penny, very small, and that has an influence on everything that happens on the Earth, on our daily lives, on the scales of the Earth. That's the comparison of the size of the black hole with the whole galaxy. So this was discovered 30 years ago, approximately. And like I said, it was surprising. And we do not know why the black hole has a strong influence on the galaxy. So that's something we are studying right now. And I am studying that correlation. I'm trying to understand why, or the ways, the physical processes that are responsible for the coevolution of supermassive black holes and galaxies. And this is related to the two proposals that were accepted by NASA for observations with James Webb. They are related to objects that we call galaxy mergers. And you can see here a collage of images. There are 12 images of galaxy mergers. They are just galaxies interacting with each other. And I always say that these are the most beautiful astronomical images that you can see because they show what we call the cosmic dance of galaxies. So galaxies interacting in different ways, different morphologies, and they just look beautiful through powerful telescopes. So I'm studying all these objects with ground-based telescopes and also with Hubble, and in the near future with James Webb. And I'm interested in objects like the one that you see here. These are results from Hubble, where you see two supermassive black holes interacting with each other. That's what you see as here, as it says northeastern nucleus, southwestern nucleus. Those are two black holes interacting with each other in one galaxy that is merging already. So all the gas that you see here is ionized gas, and it produces a very beautiful morphologies that we call the butterfly nebula. And with JWST, we will be able to study the motions of this gas. So that's something that was not possible before. So I'm going to study the motions of all these gas with James Webb, and then understand how the two supermassive black holes merge. Now, this is very important for two reasons. One is that we have never observed how supermassive black holes merge. In fact, we don't even know how this process takes place. There is some theories and simulations, but we had never observed that with real data. So I'm going to observe objects that have already merged and that have a black hole that was kicked out from the center. That's what we call a recoil. So observing those objects will tell us that the two supermassive black holes were able to merge for the first time. And then we can obtain many physical parameters about this process that will be very important for physics in general. And the second reason is that we believe that supermassive black hole binaries are the most powerful sources of gravitational waves in the universe. So gravitational waves is something that we detected for the first time 5 years ago. And actually the group or the collaboration that detected gravitational waves won also the Nobel Prize 2 years ago. So it is a very important field in physics right now. But again, it's a new field that we do not understand very well, the production of gravitational waves, the characteristics of gravitational waves, and even if we will be able to manipulate them in the future. So there are many open questions about these new waves that we detected 5 years ago. And that is something that I will be able to answer with my projects, or to contribute to our understanding of gravitational waves. And this is an example of something that we will be able to do with James Webb. These are maps of the central regions of galaxy mergers. And there are many things that we can study here. I'm not going to describe this in detail, but I just want to show you something that would be similar to what we will observe with James Webb. Several species of gas, molecular gas, ionized gas, stars, and velocity maps. Okay, so that was my last slide. I will just leave you with some of my information. Like I said, I lead the Observational Extragalactic Astronomy Group at the University of Memphis. We do characterization of environments around supermassive black holes. And if you are interested in learning more about my research, or joining my group at the University of Memphis, or you know someone who is interested in astronomy, please let them know that I'm always hiring students, undergrad students and graduate students for my research. Okay, thank you for your attention. And that was my last slide. So now we go to questions and answers. Now there is a question here. It says, when galaxies merge, do they stay merged? Well, the answer is yes. When two galaxies merge, then the final product actually is a new galaxy. So imagine you have two different galaxies orbiting each other in this cosmic dance. And when they merge, then the product is a completely new galaxy with new properties. It can be a spiral galaxy or elliptical or many other morphologies. But at the center of that galaxy would be a supermassive black hole that would be the combination of the two progenitor supermassive black holes. And also, when you say a black hole is an object, does that mean that it's tangible and could be touched? Well, that is something we cannot know right now, because we cannot travel to a black hole, or we cannot really send missions to black holes. So we do not know what will happen if we touch a black hole, or we enter to the domain of the black hole. So that's the answer. But simulations and theory suggest that when a black hole is formed, then there exists a last stable orbit where matter and energy still exist as we know it and we can see it. And that is the part that we could travel and is tangible. Inside the black hole, like I said, we don't know what happens inside the black hole. I always do actually this joke that I say that in the universe, the only region where it is true, this sentence, that what happens in the black hole stays in the black hole, is in the black hole, because it's impossible to know what happens inside the black hole. Okay, now another question. What is the process of submitting a project to be used for the Webb Space Telescope? Okay, so this is a process that has been very successful for NASA for the past 20 years, approximately, or maybe more, where all astronomers in the world submit a proposal to NASA. So you have to write a research proposal. You have to explain why your project is interesting, what you are going to do with the data, what is the transformative science of this project. I mean, would that be important for the society or for other astronomers? What would be the impact of your work? So you have to describe all these things. You have to convince other scientists that your science or your project is crucial and very interesting. So you write that proposal, and then a group of scientists, a group of experts get together for a couple of days or for a week. Now we're doing this remotely due to COVID, but still is the same process. The group of experts get together and they discuss all the proposals. So for example, for James Webb, we are going to do cycle 1 of observations starting next year. And there were more than 1,200 proposals. So all these experts, there were different teams who read all the proposals, and then they discussed all the proposals, and only, I think, 10% or something around 10% or 20% of the proposals were selected. So as you can see, it's a very competitive field. And that's the process. Then when your proposal is accepted, you are very happy because you will receive data from the most powerful telescope ever built. Okay, another question. How did you become interested in astronomy and decide to pursue it as a career? Well, in my case, which I think is a similar case for many astronomers, this is something that you have when you are a child, when you're a kid. It's a motivation that you have when you are, I don't know, 10 years old, 12 years old. For me, it happened around that age when I was 12, 13 years old. I had the opportunity to travel to a small town outside of Mexico City where it is very dark at night. There is no light pollution. So you can see all the stars and maybe nebula and the Milky Way just with your eyes. And every time I was going there as a kid, I was fascinated with all the objects that I could see with the stars and nebula, planets, etc. Well, we can see the planets in the solar system, Mercury, Venus, etc. And then I said, I want to know more about those objects. I want to know more about the universe. So I had always that motivation. I was always fascinated with space, basically, all the objects, all the aspects and objects related to space. And then I realized that in order to know more about space and the objects in the universe, I had to study physics and mathematics. Those are the two most important areas. But it turns out that for me, they were also the subjects that I enjoyed more and I liked much more at school, in elementary school, middle school, high school. I would always come home and do my physics and math homework first, and then leave everything that was related to literature and social sciences at the end, because I was really not interested in those subjects, or I was not motivated. So I would say that those are the two most important aspects. You have to be motivated and like space and the universe, and be good at physics and math. And that's what you need to become an astronomer and or to do a career in space sciences in general. Okay, now another question. Do you think the Milky Way might merge one day? The answer is yes, and we know very well how it is going to happen. So we have observed our neighbor galaxy, which is the Andromeda galaxy, is the closest galaxy to the Milky Way. And through several observations, this is something that is confirmed. We know that Andromeda is moving towards us. So the Andromeda galaxy is coming towards the Milky Way, and the Milky Way is moving towards Andromeda. So the two objects are approaching each other. So if we follow their orbits and their velocities, then we can predict what is going to happen in several millions of years from now. And we know that the two galaxies are going to merge in a time scale of 1 billion years. So we still have a lot of time until that happens, but that's a fact. The two galaxies are going to merge in the future. Now, how much mass does a supermassive black hole have approximately? Thank you for this question. So we know that black holes have masses that can be grouped, or that we can group in two different regimes. So we have two groups of masses. We have what we call stellar mass black holes, and the other group are supermassive black holes. The stellar mass black holes have masses between 3 to a few tenths of solar masses, so the mass of the sun, so 50 suns approximately. And supermassive black holes have masses of approximately 1 million to 10 billion solar masses. So that's why they got their name of supermassive, because they have masses of millions of suns. Those are the two regimes. Now, in between, we haven't observed any black hole with masses of, let's say, 1,000 solar masses or 10,000 solar masses. We call those objects intermediate mass black holes, but we haven't really confirmed any intermediate mass black hole. So astronomers are familiar with those very low mass black holes, like 50 solar masses, and then millions of solar masses. And those are the masses that we have observed. And also, we know how those objects are formed. We know that stellar mass black holes, they get their name because they come from stars. So some stars, massive stars, when they die, they become black holes. So we know that process very well. And that's how these black holes of 50 solar masses are formed. And the supermassive black holes, we know that they exist because we observe the gravitational influence at the centers of galaxies. So we know very well how these objects, or we have a very good idea how to find them. That they exist at the center of galaxies or stellar mass black holes when stars die. But intermediate mass black holes, we do not know how to find them. I mean, there are some theories, there are some projects aimed to detecting intermediate mass black holes, but they are still very difficult to find. Okay, can a galaxy merge with a black hole? Well, yes. I mean, if you have two galaxies and they merge, then immediately, I mean, because we believe that all galaxies have supermassive black holes at the centers, then the black holes will merge eventually, or that's what we believe with theory and simulations. Now, the galaxy, it can be two major, we call that a major merger, where we have two large galaxies merging, but we also have minor mergers, where we have one very large galaxy and a small galaxy. It can be what we call a dwarf galaxy, and that can be mostly just a black hole. So the answer is yes, it is possible that we can see a galaxy merging with a black hole in a dwarf galaxy, for example, or in a minor merger. Now, how long will the Webb telescope be operational? So I think it will be operational, so its lifetime, I think it's more than 10 years, between 10 to 15 years. But I'm not 100% sure, because sometimes, and what happens with these satellites and these telescopes is that maybe they have more fuel than we predicted by calculations here on Earth, which is actually something good. I mean, NASA, the engineers working on this project, they always try to have a plan B, plan C, plan D, etc. So they predict or they suggest a lifetime of the telescope, but in many cases, they live longer than it was predicted. So that has been for most of the NASA telescopes. In the end, they live longer because they have still resources, like I was saying, fuel, electricity, and then they work for more time than it was expected. So I would say it's around that time scale of a decade or a little bit more than a decade. What are you the most excited to learn about through the web? Well, as an expert on supermassive black holes, of course, I am very excited to learn more about the lives of supermassive black holes. But I have to say that for the society in general, I mean, the impact of James Webb, I think it's what NASA always describes. And NASA says that it's related to the origin of galaxies, the light from the first galaxies in the universe, and the possibility of detecting life in other planets. So I think as a person or someone who's interested in science and astronomy, I think those are the two most important science goals. So that we see light from the first galaxies to learn more about how the universe, I mean, where we live, was formed, and then detecting life in other planets, because that, as you probably can guess and you know, will have several implications for humans, for our societies. Detecting life will change many of the things that we, I mean, that we take for granted here on Earth. I mean, it will mean that life can exist in other planets that is not on Earth, and probably will have also impact on the societies, on social aspects related to politics and religion and everything. I mean, it will touch all areas of mankind. So I think detecting life is a very exciting topic from James Webb. Okay, there is one more question. What is the smallest type of black hole? So that's a very good question, because in theory, everything can become a black hole. Everything that has a mass can become a black hole. I mean, my phone can be a black hole, a table, or I can become a black hole if there is a force that is so strong that compresses all my atoms and all the molecules in my body to a volume that is very, very small. I mean, almost zero. So if that force exists, then I will be a black hole, or my phone will be a black hole, or the table will be a black hole. But of course, that force does not exist anywhere in the universe. Maybe we can do something in particle accelerators, where they are trying to accelerate particles. And one of the predictions is that they can create micro black holes, but that hasn't been done. But this force only exists in the interiors of stars and at the centers of galaxies. So there, we can find this gravitational force that is so strong that compresses millions of masses or several solar masses into small volumes. And that's how we know that black holes exist. So in principle, you can have micro black holes if you can get this force of gravity so strong. But like I said, that doesn't happen every day in our lives. I mean, you don't see that, and that doesn't happen here on Earth or in many regions of the universe. It's just when a star dies or at the centers of galaxies. That's what we believe. All right, so I just see here in the chat that says that there are no more questions. So I would like to thank you for your attention, and I will stop the live stream now on Facebook. So I hope that you are more interested in the James Webb Space Telescope, the things that we can do, and mostly that you are interested in astronomy and science in general after this talk. So I would like to thank the Mississippi Museum of Natural Science for this opportunity. And I wish you, I hope you have a good weekend. Enjoy the rest of your weekend. Bye.